So, in part B of our look at secondary bonding, we are going to look at the interactions between molecules. We're going to learn about three really important different interactions between molecular compounds, or those small covalent molecules. These interactions, this stuff also sometimes called secondary bonding, is going to be crucial for so many things that we're going to do over the next 2 years, and if you go on and do further study in chemistry or in biology for that matter. A lot of this is what controls the structures of proteins and DNA, and all that sort of thing is controlled by these secondary interactions between molecules. So this stuff is going to be critical to lots and lots of things that we're going to do in the coming years. Let's get into it. So there are three types of secondary interactions that we're going to learn about. Dispersion forces, which occur between non-polar molecules. Hence why we've been looking at whether molecules are polar or non-polar, because that's what underlies what type of secondary interactions form. We're going to look at dipole-dipole interactions, which are between polar molecules. Oops, sorry about that. And we are going to look at a special case of dipole-dipole interactions called hydrogen bonding. So these two here are both forms of dipole-dipole. They're quite similar, but usually because these ones here that involve fluorine and hydrogen, oxygen, hydrogen, nitrogen, hydrogen bonds form particularly strong dipole-dipole interactions, we tend to classify them separately. But in terms of the concepts that underlies them, it's basically the same in both cases. Let's start by going back to dispersion forces. So, dispersion forces form within a molecule. So these little blobs here, or these elliptical shaped blobs, are all meant to indicate a very crude representation of a molecule. And the little black dots are all the electrons that are spinning around the atoms in that molecule. Because electrons don't just stay in a fixed spot. They are generally more likely to be between two atoms if they're bonded, and they'll be spinning around in pairs. I won't try and draw the pairs, that gets a bit complex. But the atoms are basically moving around constantly as they orbit the atoms, the nuclei. And what you can eventually get happen is, just through that random spinning of electrons, is that you'll end up with a case where momentarily there will be more electrons on one side of the molecule than the other. And when that happens, that side of the molecule will temporarily, it's not there all the time like in a dipole, like in a polar molecule, but you'll get, if you like, this temporary dipole form. So I'm running out of a bit of space here. We can get these temporary dipoles formed due to the random movement of electrons. Now, once this happens, this atom here has got lots of electrons at this end. So those electrons, like charges will repel, will tend to push all of, not all, but the majority of the electrons are more likely to get pushed down to this end of the molecule, this side of it, and we are likely to have a lot less electrons at this end. So that's going to mean that this end is also going to have that negative charge, and relative to that, this end will be a slight positive charge. And I could have done the same here. Because most of the electrons have gone to the other side, this end is more likely to have a positive charge. What does that mean? That means now these two temporary dipoles will be oppositely charged, and we will get an attractive force here. So we get some attraction here, which is basically what a bond is indicating. A bond line is an attraction between either two molecules or two atoms earlier on. And this thing happens right through the structure. Because there's a lot of negative charge at this end, in this one, most of the electrons are going to get pushed down to this end. So we're going to have a lot more electrons down here, and not quite halfway yet. And on this side, then we're not going to get that many electrons. So we get this temporary dipole set up here. And if we go on, we can see a similar thing here, negative here, so negative up above. So the electrons will tend to push up to this end. And be repelled. So I'll just show that with the cursor, the laser pointer in a sec. So yeah, that negative charge from there here is going to make those ones try and get further away, so they'll push to this end. So we set up at that other temporary dipole here with a negative and a positive. And so this negative and positive here will attract. The same thing will happen here between the positive and negative end. We've got a positive and a negative here, positive and a negative here, positive and a negative here. So all these sort of temporary bonds will start to form. They will always be forming and breaking and forming and breaking. And in a sense, that's what's happening in a liquid. It's able to form bonds and break bonds. So it's probably started almost with the hardest one to explain, the dispersion forces, but hopefully that gives you a bit of a picture of how this random movement of electrons can lead to these temporary dipoles forming, which can lead to these attractive forces that lets even non-polar molecules be able to stick to each other, so that things that are non-polar, like oxygen gas, it doesn't stick very strong to each other. That's why oxygen is a gas at room temperature. But if you can make it cold enough, you can slow these electrons down enough that you can get these dipoles to be strong enough at very low temperatures to hold oxygen molecules together, either in liquid oxygen or, if you go cold enough, even solid oxygen. So, in summary a bit, this is the weakest form of secondary interactions. Therefore, the substances have low boiling point and melting point. It doesn't take much energy to break up these bonds. However, the strength of these, so the strength of these dispersion forces increases as the number of electrons increases, which increases as molecular mass increases. So, if you increase the molecular mass, you increase the number of electrons, therefore the melting point and boiling point will increase. So something like iodine, iodine just contains two iodine atoms in a non-polar bond. However, it can, sorry, I was just looking for the right coloured pen. Draw here an iodine. That would be an iodine molecule. It'd be non-polar. But iodine has a very large molecular mass, a high atomic number. Therefore, iodine is actually a solid at room temperature, although you don't need to warm it much to turn it into a gas. It doesn't tend to turn into a liquid. So that is dispersion forces. The second form, which is hopefully going to get a little bit simpler, is dipole-dipole bonding. We've got hydrochloric acid here. The chlorine is more electronegative. Hang on, I don't want to write that there. Write it here. So that has a slight negative charge. The hydrogen would have a slight positive charge. And then if we get another hydrochloric acid come along, like this would be the opposite. So we will get these oppositely charged ends of the molecules So the negative end and the positive end and the negative 10 will attract each other. If we had another hydrochloric acid down here, positive end, negative end, once again we would get these interactions like this. So these will tend to hold those molecules together, meaning that they have a moderate strength. So these, because they're permanent dipoles, they always exist because of the polar molecule. They're stronger than the dispersion forces, and things that dipole-dipole bond will tend to have moderate boiling point and moderate melting point and boiling points. MP is melting point, BP is boiling point. Now, probably the most common one and the most interesting one we deal with is hydrogen bonding. And as I said before, that's a special case of dipole-dipole interaction, and it occurs when we have FH, OH and NH bonds. These are, if you like, the three smallest period 2 elements. Hydrogen is also a small element which helps these form much stronger dipoles. We don't need to understand the detail of that. But if you can imagine water, another water comes along, I might draw a couple more coming along. Another water comes along. Water is polar, so the oxygen end will be negatively charged, the hydrogen end will be positively charged because it's got a lower electronegativity. The oxygen obviously had the higher electronegativity. So if we put in all the polarities of these bonds, we get something like this. Hence why we've been so concerned about learning about polarity. And then what we will see is these oppositely charged ends of these bonds will all attract each other. And they are the secondary interactions that hold all the water molecules together in liquid water or even in frozen ice water. Obviously, if we boil water to 100 degrees, there's enough energy to break all these bonds. We set all the hot water molecules free, if you like, to randomly dance around the room. So that's when water would boil, if you go back to learning about the particle model in previous years. So, a lot in that slide. Really important that you do understand this stuff. Where you get dispersion forces, oops, that's not a cursor, where you get dispersion forces, where you get, I'm just checking I haven't rubbed out something I shouldn't, where you get dipole-dipole bonding and where you get hydrogen bonding. And also you understand that the dispersion forces are the weakest form, dipole-dipole are the moderate form, and hydrogen bonding is the strongest form of secondary interaction. Thank you.